based or the percentage.
Very last session of the day, and we're all hanging in there. And so this is work that I did with Young Fu, and it's very nice to have, be able to collaborate with Vidya and others. And so now I'm going to speak about some of the theory and other considerations that went into our proposing the model that, as you can see, there's been very exciting work done when we put out this paper already. So another interesting aspect of our work other interesting experimental systems that our work touches on is also the field of interface superconductivity. And that is a phenomenon in which we have materials that by themselves do not exhibit superconductivity or superconduct at much lower temperatures. And when you put them together at the interface, they do exhibit superconductivity. One is, of course, a celebrated example of Aleo STO. There's been a lot of activity recently. And even more recently, there's been some very exciting new work in which certain materials, for example, single-layer iron cyanide, are put on STO, and they've seen really astonishing results, a TC of over 100 Kelvin, and there's more results coming out. So, of course, all of this begs the question of why and what is happening, what is going on at the interface. It turns out also that these materials, that these topological crystalline insulators that Vidya spoke about, also are part of the story, much older actually, that these experiments were done decades ago. And in these materials which you'll recognize, that telluride, tin telluride, when they built these super lattices, again, they also saw in their single films are not conducting. When you put them together, you start to see that these multi-layers can superconduct with a TC of up to 6 Kelvin. And this work was subsequently repeated over these decades, and then they expanded it to different families in which they have down to bilayer systems now, different materials always in the same family. And so then you can start to really identify what contributes to this interface superconductivity. This is the, let me know. Yeah. And so this of course begs the question of, of why does superconductivity emerge at the interface, and can we, describe or understand the origin of the mechanism behind this? And of course, as pointed out, that these materials that we're looking at today do fall into the class of topological crystalline insulators. Vidya gave a beautiful introduction to them, so I won't need to spend much more time on that. But what we really want to look at here is look at how a model of the effects of strain on these Dirac fermions at the surface of these materials give rise to pseudomagnetic field Landau levels, consequently a large density of states that then can contribute to an unusual superconductivity. And of course, we want to compare our theoretical model to the experiment and continue to give some other experimental predictions that could be used to verify a proposal, and then followed by wrapping up. So, of course, now you've already seen these pictures of this rock salt structure and this family of materials, of this 4-6 semiconductor material family class, in which you do have these surface states on different surfaces, and under different forms of mechanical or chemical pressure, then these materials, if they are not already topological, can undergo band inversion through these mechanisms to become topological, and they're protected by mirror symmetry and U1 charge conservation, as Vidya pointed out, in contrast to regular TIs, which is time reversal and U1. And then of course, beautiful work done with Vidya to characterize the surface states in this material, and in particular, we will be focusing today on the 001 direction, because as I'm going to explain, that is where we see the strongest difference of these surface states with regular TIs, because there we actually see surface states that are tunable. And this is tunability that we're going to exploit to look at the effects of strain on this surface. So then this is data by Zahid and Vidya, just to note how there's these two, they come in pairs and they lie along two orthogonal mirror axes, restricted by four-fold rotation symmetry. So this is a nice picture from Zahid's group, in which it illustrates very nicely the differences between regular TIs and TCIs, just so that we can get a feel for what we can expect in these materials. The Dirac points in regular TIs occur in odd numbers, and they are pinned at the high symmetry points. And so under time reversal, it goes back into itself, and hence under something like strain, there is going to be no effect. Whereas in these TCIs, they are not constrained to lie along the high symmetry points, and as we saw, that they can be tuned along this mirror axis. And this is a tunability, and since they always occur in pairs, which means that under a field such as strain, they can move oppositely, such that overall it does not bring time reversal symmetry, but they can move in opposite directions along this mirror axis in a continuous fashion. And again, this tunability is going to be what is going to give rise to the kinds of effects that we can hear. So Vidya already showed this data, and this is showing how through a different mechanism, changing the alloy composition of this material, that one can shift the position of these Dirac cones closer and closer towards the zone boundary, so that at the transition point, because it transitions from a topological material to a trivial material, then they disappear. And this is alloy composition, but we get a similar effect from strain. So then to see what strain does, we can simply we can look at the symmetry analysis to understand its effect. And if we do preserve all four-fold symmetry, then we naturally expect that strain pushes the Dirac cones in an equal manner towards or away from the zone center, and continues to preserve the four-fold rotation symmetry. And if we break down the four-fold rotation to two-fold rotation, then naturally we do expect the Dirac cones, to have a pair shifting towards the zone center and a pair shifting away from the zone center. And if in this case we break the mirror symmetry, such as through shear strain, then naturally we do expect the Dirac cones to move away from the mirror axes in such a fashion. And so this is the way in which we can parameterize different kinds of strain that we can apply to this system, and hence alter this. And as Vidya pointed out, that the movement of these Dirac cones is similar to graphene. However, because of the crystal symmetry in these materials that is different from graphene, in graphene there is only one way in which strain can rotate these Dirac cones, whereas here we have three independent ways in which we can manipulate the Dirac cones in these materials. This symmetry analysis was supported by ab initio calculations, in which here they did calculate how different types of strain will alter and change can cause firstly a phase transition into the topological phase, and then subsequently